So thank you very much for the very kind introduction. So today I'm going to share with you some of our work on molecular functional materials. But of course, I have to thank the organizer, EmTech, for giving me this opportunity to share with you some of our work. So I'm a chemist, but I'll try to make it simple. And actually, it's not that terrifying in terms of looking at molecules. I have represented with cartoons instead. So if you look at the world energy consumption, right now, the annual global energy demand is something like close to 13 terawatts, and around 80% is really coming from the burning of fossil fuels. And by the year 2050, you need something like 27 to 33 terawatts. And so there's really an energy gap of another 14 terawatts that we need by the year 2050. And so, of course, people were sort of saying that, so what are the big challenges? Of course, we are facing the upcoming depletion of fossil fuels. Of course, some people would argue we still have another 50 to 60 years of oil, natural gases, and we still have methane clathrates in the deep sea, and then another 200 years of coal. But even if we have plentiful of these sort of resources, the problem is when you burn it, you are going to produce carbon dioxide. And this really creates the problem of global warming as well as climate changes, although some people didn't believe in it. So anyway, but if you look at the world energy consumption, actually China has become one of the largest, and in fact, it's the largest consumer of energy in the world. And so how can we sort of face this sort of challenges? I believe there's an urgent need for us to come up with a low carbon or carbon neutral source of economy. And so what are the solutions? Of course, there are many solutions. We just heard from Dawn about battery storage, energy storage, and so on. And so we think that there must be new sources of clean, renewable energy. And of course, there are many options. And we are particularly interested in solar because the amount of sunlight that falls onto the Earth in an hour is already sufficient to provide the energy that is demanded in 1 year. But of course, this is based on an assumption that every inch of land is covered by a solar panel, which is highly unlikely. But still, it's pretty attractive. And another way that you can think of is why don't we make use of more energy efficient processes, particularly for lighting, because right now, lighting actually take up around 20% of our energy. And if we can replace it with more energy efficient processes, this will be something very helpful in terms of energy saving. And as I just mentioned, around 20% of our energy is really used in lighting purposes. And we are really, a lot of places are still relying a lot on a very old technology. Some places are still using the incandescent lamp, which has been created for more than a century. And actually about 90 to 95% of the energy is really wasted as heat. So what if we can replace it with some more energy efficient processes like organic light emitting diodes for lighting purposes? Then this will help to save energy. And obviously, when you have organic light-emitting diode materials, you can really print it onto a very thin, flexible substrate, so you can have a very nice, aesthetically interesting sort of decorations. And you can think of all the different opportunities with this white organic light-emitting diode lighting. And obviously, when you want to make the white light, you need the three primary colors, the red, the green, and the blue. You mix them, you get the white. Or alternatively, you start with the yellow and the blue. You mix them together, you also will be able to create the white light. Now, besides that, since you have the three primary colors, the red, green, and blue, then of course you can also make full-color flat panel display. And of course, it's already on the market, like the Samsung tablets, as well as the mobile phones and many others. And of course, there are the curved TVs that you can now see on the market. And all these are really very interesting developments. And if you look at the OLED display market, actually it's going to hit something like 57 billion US dollar by the year 2026. And for the lighting market, you are going to look at something like 6.7 billion US dollar in the year 2023. And of course, there are, whether it's the lighting or the display industry, there are a lot of very new, exciting developments like the virtual reality and things like that with the AM OLED. Now, but all these boils down to the fact that you need really the material. So I'm a chemist. I work a lot on the OLED material. And if you look at the material alone, by the year 2021, the market will probably be forecasted to reach something like over 3.3 billion US dollars. So this is really a huge market that's going on. Now, so what do you do with the materials? So actually these materials, if we go back to look at the solar cells, actually they absorb the light, they generate an excited state, and then if you can separate the charges, the electron and the hole, and then you collect it at 2 different electrodes, this is really the basis of how a solar cell works. And actually we are inspired by a photosynthesis where we have the very famous C scheme. And so essentially you want to separate the charges, and you want to make the materials to match the solar spectrum as much as possible. Now, instead of collecting the electron and the hole at 2 electrodes to give you the solar cell, you can also harvest onto the electron to do reduction processes. For example, reducing water to hydrogen gas. You can also reduce carbon dioxide to useful chemicals. On the other hand, you can make use of the hole for oxidation purposes, to oxidize water to oxygen, to oxidize methane gas to methanol, which is much more easier for transportation, and so on and so forth. So there are a lot of things you can do with these sort of materials. And actually, as I mentioned, the principle is essentially you shine light, you generate an excited state, and then there's a charge separation, and then you collect the electron and hole, trying to sort of slow down the recombination of the charges. Now, but as time would not permit me to say too much about that, so I will mainly concentrate on the organic light emitting diode materials, the OLED materials. So essentially, what you have is that you need luminescent materials. So again, you shine light, you generate excited state, and then when this excited state falls back to the ground state, they will release the energy as light. And then obviously, as I said, you have the 3 primary colors, the red, the green, and the blue. Then you can make white light, or the yellow and the blue. And then you can also have the full color display. And when you have luminescent material, actually you can also use it for bioimaging, for sensing purposes, and so on and so forth. And actually the principle of an OLED is just the reverse of the solar cell. In this case, you inject an electron, you inject a hole, they recombine, give you an exciton that emits the light. So as a chemist, as I said, we have been manipulating molecules, right? We synthesize new molecules. They are easily processable. We will sort of create these molecules so that we design it to perform a certain function. So it's function by design in a way. And so what is on the market for these phosphorescent OLED materials? Mainly people have been working on the iridium complexes. So iridium metal centers is a very precious metal, is not earth abundant, is very sort of, is non-earth abundant, and actually that was first used by UDC, Universal Display Corporation. I'm sorry that this is a chemistry, but let's represent it with some more interesting cartoons. So this is another type of these iridium compounds that will give you the blue light, particularly the deep blue, because you need the blue is the most challenging part. So this is really the basic molecule that we are looking at. Now, we have carbon, nitrogen, carbon, nitrogen, carbon, nitrogen, sort of surrounding the metal center, iridium, in the middle. And actually, if you look carefully at these 2 molecules, if I represent the nitrogen with a blue ball and the carbon with a red sphere, then you see that there are different types of arrangement, whether it's the red, blue, red, blue, red, blue on the left, or whether it's the red, blue, blue, red on the right. Actually, they are so-called isomers. They have different arrangements. And actually, the one on the left actually is more strongly luminescent. This is the one that people use to use it as an OLED material to make the device. But actually, these are small molecules, so they need to sublime them to do vapor deposition to make the device. And during the vacuum deposition, sometimes rearrangement of the molecules, rearrangement of the atoms would occur to give you the molecule on the right-hand side. And that one is very, very weakly emissive. So there's a problem of the rearrangement during the processing of these devices. And this is something that we don't want, because you turn something originally brightly emissive now to something that is not so emissive. So that runs into a problem when you have 6 atoms surrounding the metal center. And now we are interested in 4 coordinate species. What we mean by 4 coordinate species is that we have 4 atoms surrounding the metal in the center. Okay? And now what we did is that they are not susceptible to this rearrangement of the atoms. And so you don't run into the problem that was encountered with the commercially available material. And we can also link these atoms, the carbon and the nitrogen together, three of them together to make something like a pincer type of molecules. And so we make a lot of these molecules. But then when we talk about materials, it's not due to one single molecule. Actually, it consists of a large assembly, an ensemble of many, many molecules. And so how you can pack the molecules one with respect to each other to align the molecules actually will make a huge difference in terms of the charge transport properties as well as their optical properties. So we as chemists can manipulate these intermolecular forces so to put the molecules in an order as we would like it to be. So my group actually work a lot on, so it's the same molecule, just the way they pack, whether the molecules is packed in a linear fashion in the top or whether it's packed in a zigzag fashion in the bottom, would already be able to make materials that have very different colors. The one on the top with linear array is green in color, the one with zigzag is red in color, and they have also very different emissive properties as well. They emit different colors as well. We can also make molecules and put them in an order to form nanotubes. So as on the left-hand side, on the right-hand side, we introduce three very bulky groups there. Then they don't form nanotubes. They start to form nanoribbons. And they have also different colors and different emission colors as well. So we can really play around to tune it. Alternatively, we can add some hydrophobic groups. So hydrophobic groups means that they hate water. And so when you put this on, and then again by manipulating the intermolecular forces, we can now align them in a way to form donut-shaped structure or to align them in a rod-like structure. So with different morphologies, we will pack the molecules in different ways to give different morphologies as well as different charge transport properties and different emission colors as well. So we have a way to manipulate and control that. And we can also make, again, the same molecule. We can put them in different alignment, different packing, and you can see the color change all the way from red, orange, yellow, green, and blue. Different colors, same compound, but how they pack would already matters. And the red one actually consists of vesicles, the blue one actually consists of rods. So we have ways to manipulate, and also by changing the carbon chain length there, we can also make them from sheet-like structure to form cylindrical rod-like structure with different emission colors as well. So we make a lot of these molecules, and this is one example. I'm sorry, there was something wrong there. So there should be the green emission coming from this, a brightly green emission coming from this molecule, and we can make OLED devices. This is small molecule by vapor deposition, and to reach pretty decent performance. And more recently, we work on solution processable material because then you can really print it, sort of row-to-row printing, and it's a very cheap way of processing. So we work a lot on solution processable materials, and as you can see, this has very good performance in a way that now is reaching a very high performance, like current efficiency over close to 60 candela per ampere with extremely high external quantum efficiency for solution processable materials. Now, besides platinum, so platinum is still quite expensive and not earth abundant. So you have iridium, it's more expensive, platinum is cheaper, and now we are moving towards gold. It's a little bit even more cheaper, and it's more abundant as well. And it's more environmentally benign. So we have gold compounds, we have the small molecule. Again, we do vapor deposition to make devices. We can make solution processable materials. Again, this is a very nice saturated yellow color that we made with, again, very decent performance. Now, but one of the problems with these phosphorescent materials or metal phosphors is that when you have a very high brightness, usually the efficiency would drop tremendously. We call it efficiency roll-off. And with our compounds that we made, we're able to improve the charge balance and so on. I don't want to bother with details. And with this one, even at a luminance level of 1,000 candela per meter square. So what is 1,000 candela per meter square? Is within 1 square meter, you put 1,000 candles there. And the brightness of that 1,000 candle within 1 square meter is that 1,000 candela per meter square sort of brightness. And even at that sort of brightness, the quantum external quantum efficiency roll-off was less than 1%. And this is really one of the record high values that we can show with solution processable materials. Now, besides that, instead of linking 3 atoms together, we can link all 4 atoms together to make the one on the furthest right. And by doing so, actually, we make the molecules more robust. By linking every atom together surrounding the metal center, we improve the decomposition temperature by more than 100 degrees to over 470 degrees. And also, the emission becomes more brightly emissive. They have a larger emission quantum yield. They are much brighter in emission. They are more robust. They are less likely to decompose by this sort of chemical modification. And we were able to make yellow devices out of this. Again, pretty decent performance, as well as reddish-orange type of devices out of these materials. And all these materials were really made in Hong Kong. We have the first discovery of these luminescent gold compounds, and now we're able, I'm sorry again, something happened. So we're able to make all the way from blue, green, yellow, red, so all that disappeared, I don't know why. So I'm sorry about that, but we are able to make a whole array of different colors right now with very nice performances. And to end the talk, actually, I've only shown you one facet of molecular materials where we make use of it to make devices, like OLED devices, but actually they can also make organic memories out of that. We can make static RAM out of that. We can also make optical memories out of that for data storage and so on and so forth. And this one, just by a small trick in the sort of chemical modification, we can make bistable binary memory versus ternary memory. And of course, ternary memory with a larger storage capacity, because the storage capacity, digital data storage capacity, varies with 2 to the power n. So we have a much higher density sort of storage system. And with that, I'd like to thank all the students and postdocs with different generations of students working on this work, and particularly Dr. Maggie Chen. And I'd like to thank the funding agency, particularly the University Grants Committee Areas of Excellence Scheme and the Theme-Based Research Scheme, as well as the Innovation Technology Commission. And actually, our gold work was first sponsored by World Gold Council from Switzerland. And of course, the University of Hong Kong for financial support. And of course, thank you very much for your kind attention.